Okay, so we're just gonna get straight into it. Take five of the day. Um, I've been having some computer issues or connectivity issues on my laptop in my office. I reset up the Marmaday validator machine. I'm now using that to try and stream, and it's pretty set up. It's quite nice. Um, Computer issues or connectivity issues on my laptop in my
Okay,
office.
I mean the audio
I
seems to be good enough. Um, so yeah, I'm just gonna try and relax and get into it and get started here in a different room in the in the house. So I got after the four attempts this morning, I got to chapter 1.4, 1.3. And I do I set up Zotero over lunch as well, and so now I'm able to do fun things like this and like highlight parts of the equation to make things easier for me, which is very exciting. It's already proven to be quite useful. So now it's the paper is open in Zotero. Um, so let's just get into it. Looks like everything's working. So you may have encountered clock arithmetic in grade school, where after you get to 12, the next number is 1. This leads to odd-looking equations such as 6 plus 9 equals 3 and 2 minus 3 equals 11. These look strange, but they are true using clock arithmetic. Since, for example, 11 o'clock is 3 hours before 2 o'clock. So what we are really doing is first computing 2 minus 3 equals negative 1, and then adding 12. So it's kind of a way to think about modular arithmetic. If you're doing some addition or subtraction mod 12, you can kind of do the operation first, get your answer, and then add whatever the mod is. So 12. Similarly, 9 hours after 6 o'clock is 3 o'clock. So again, you can do the same thing. 6 plus 9. This time, because you're doing addition, you subtract the mod, you get 3. So it's the congruence, I guess the inverse or whatever. The theory of congruences is a powerful method in number theory that is based on the simple idea of clock arithmetic. Let m be greater than or equal to 1 be an integer. So you have m being this positive number, has to be 1 or more. We say that the integers a and b are congruent modulo m. So these two other integers are congruent modulo this positive integer if their difference, so a minus b, is divisible by m. So if you have 6, 9, and 3, if 3 is the m, and you have 6 and you have 9, they would be congruent. Because if you took, let's say a was the bigger number, 9, and you minused it by b, which is 6, you'd get a number which is 3, which is divisible by 3. We write A, 3 lines, almost looks like an equal sign. B, I sometimes say equals by accident when I see it. Congruent, not equal. And then mod, some modulus. To indicate that A and B are congruent modulo m. The number m is called the modulus. Our clock examples may be written as congruences using the modulus m equals 12. So 6 plus 9 equals 15, right? That's the actual number, but it actually equals 3 mod 12. So if you're doing this in the sense where everything has to be mod 12, you only get to have 3. You don't get to know how much the actual number was. And a lot of numbers could be 3 mod 12. And 2 minus 3 it technically, you know, in our normal everyday lives equals -1, but it actually is 11 mod 12. And so in this example, we have 11 is congruent to 7 mod 5. Since 5 divides 10, and then you would get 7 left over to get to 17. On the other hand, 19 is not congruent to 6 mod 11, since if you have 11 and you're trying to get to 19, you cannot actually do that. 13 would actually equal 19 minus 6. So modular arithmetic took me a really long time to grasp. I finally, after just staring at it and beating my head against it for many months, I feel like, oh look, I understand elementary school math a little bit better. But that's always how I've been. It takes me a while to grasp mathematical concepts generally. And that's how I just do the homework, which I'm going to start doing a lot more. I have my tablet out beside me. It's not working the best, but it's working enough. And so I'm going to try and stop maybe here and there and do some math actually like beside me. So we'll see. Actually, let me get that somewhat set up now. There you go. So maybe I will write out some of this just to make it simple. You have 6 plus 9. I'm just going to write out this real quick. Maybe not all of it, but equals 15 is congruent to 3 mod 12. I just want to get better habit of, what's it called? I got to get in a better habit of writing a lot of this stuff out. So 2 minus 3, it really equals -1, but in this weird, wonderful world that we're in now, it's actually 11 mod 12 if we're staying mod 12, but we can be mod whatever we want. So we can be mod 5, so 17 is congruent to 7 mod 5, and then, you know, it's okay, but 19 is not congruent to 6 mod 11. A is congruent to 0 mod M. Okay. I'm kind of taking notes in both places. I know you guys can't see my other notes, but and maybe I should be taking some notes from here. I was kind of just having a lot of fun reading. I'll take this one down though. Oh, it's working again. Yay. See, copying and pasting from here is just better as well than doing it from Chrome. Okay, then we have the reason that congruence notation is so useful is that congruences behave much like equalities, as the following proposition indicates. So proposition 1.13 is saying let m, which is a positive number, be an integer, and then if a1 is congruent to a2, oh, this is the stuff I gotta start. Okay, let's go. I can do this. If A1 is congruent to A2 mod M and B1 is congruent to B2 mod M, then A plus my, like I can't remember how you say it, but I understand what it's saying finally, but I still don't know how you like write it out. From my understanding, it's just like as a multiple of, so like if you took A, which is the bigger number, and you added B, or it doesn't matter, but or subtracted B, it's congruent to A 2 operated on, I guess. Oh, I guess it's the same thing. It's just the operation of addition subtraction instead of the operation of multiplication. So the additive notation, I guess, instead of the multiplicative. Oh my gosh, notation. From my understanding, makes sense. And then let A be an integer. That makes sense. Wouldn't B also be? Yeah, B is also an integer. So let A be an integer, then A times B is congruent to 1 mod M. So A equals 0 mod M, and A times B equals 1 mod M. If and only if. So this is always going to have to satisfy. And then this is only true if the GCD, the greatest common divisor of A and M, and the clock is 1. Big number. A times B, which is just creating multiples of itself. Oh, that makes sense. That makes sense. Because A times B, if they weren't GCD equals 1. Oh, that's interesting. Okay. I'm like, okay, cool. Makes sense. Actually, I need to take a note of that for sure, though. Because this... The first one wasn't that big of a deal to me. So I'm going to make sure I separate these apart. Because that one was awesome. This one was alright, but this one was like, yes. Maybe I'll even just highlight it here in my notes. Maybe in a cute purple. If such an integer B exists, so B doesn't always exist. Oh my gosh, I can add comments. Have fun with this math later. Okay. Tag. Oh my gosh. Rust. Oh my god. Just add the one tag. Okay. This is so cool. I love this so much. If integer B exists, which is the number you have to multiply A by in order to get this 1 mod M, we say that B is the multiplicative inverse of A modulo M. That makes sense. It's the number you multiply by to get the inverse, because 1 mod M would be the inverse. We say that the inverse rather than n inverse because any two inverses are congruent modulo. So you only have one of them. Proof. Aw, I like reading proofs. I don't like doing proofs. See exercise 1.14. Suppose first that the GCD of A and M equals 1. Because that's what we know. That if this B exists, the GCD of A and M is 1. So you're going to start there. Then theorem 1.11 tells us that we can find the integers u and v satisfying AU plus MV equals 1. So now we know AU plus MV equals 1. And the GCD of A and M equals 1. Okay, this looks fancy. This looks good so far. This means that AU minus 1 equals MV equals negative MV is divisible by M. So I'm guessing they just did this math and like did this equivalence and they're saying it's divisible by m, so by definition, AU equals 1 mod m. In other words, we could take B to equal U, because if we know that, where are we? If we know, where is it? Why is my brain farting me? Suppose that GCD of AM equals 1. A times B. Where's the part where it said the whole A times B? Oh, here. Sorry. It's right here. Literally, I need to like put this in red. There you go. So if we know A times B is congruent to 1 mod M, then if we have AU is congruent to 1 mod M, and that maybe I should also put this in red. There you go. So hopefully that makes that clear to me, at least for later. In other words, we can take B equals U, because B, so we always know B equals U. Okay, this is just getting really cool. So B equals U, and then we can find integers in U and V satisfying AU plus MV equals 1. This means that AU minus 1 equals negative MB. Okay, that's simple enough. It's divisible by M. So this is the part. So basically, by definition. What definition? Which definition? It's probably this definition right here. Congruent modulo M if their difference AB is divisible by M. So we know their difference is divisible by M. And so we're saying here their difference is divisible by M. So this difference, because we know MV is divisible by M, so we know this is divisible by M. So you can just what? Move 1 back over because you know it's divisible by M. Okay, so I am going to just highlight this as green. This is green, and maybe my brain will be able to track that well. So you're kind of just cheating. So you always know from the very beginning that when you're doing this AU plus MV equals 1. So once we literally know that the GCD is 1, and we know that they're relatively prime, we can find the inverse using this algorithm. Very cool. There's an algorithm for it below, so I'm excited to get to that. That was actually pretty helpful. I'm going to take this whole thing because I loved it. The whole like B equals U thing finally makes sense. So maybe just like we're going to find For the other direction, suppose that A has an inverse modulo M. Say A times B is congruent to 1 mod M. That means that AB, so A times B, move 1 to the other side, -1 equals some number times C for some integer C. This follows that the GCD of A and M, let me make sure I can follow, the GCD of A and M divides AB minus MC equals 1. The GCD of A and M divides all of this. Yes, that makes sense. This completes the proof that A has an inverse, because it only has an inverse if and only if the GCD of A and M is 1. Oh. Okay, we're just doing a proof. Okay. They didn't leave it as an exercise, and then they just did it. I remember already being confused by that before. Proposition 1.13, B says that if the GCD of A and M equals 1, there exists an inverse B of A modulo M. This has the curious consequence that the fraction B inverse equals 1 over B then has a meaningful rotation in the world of integers modulo M. Why? Because it's B inverse A? Maybe. Maybe because you could flip-flop between them. We take M equals 5 and A equals 2. Clearly the GCD of 2 and 5 is 1. So there exists an inverse to 2 modulo 5. The inverse of 2 modulo 5 is 3. This is where I gotta start paying attention. Since 2 times 3 is congruent to 1 mod 5. Because 2 times 3 is 6, and then 1 is the remainder. -1 is 5. So, 2 inverse. Okay, this is where I gotta pay attention. A inverse. So A inverse, because M is 5, so M is the modulus, and 2 is the number. 3 is the B. So 2 modulus equals 3 mod 5. Similarly, the GCD of 4 and 15 is 1. So 4 inverse exists modulo 15, because 4 is A and 15 is M. In fact, 4 times 4 is congruent to 1 mod 15. So 4 is its own inverse, modulo 15. I feel like I've read this 3 times and I'm understanding it sort of mostly now, I guess. But so exists an inverse to 2 modulo 5. The inverse of 2 modulo 5 is 3. I mean, it all makes sense. We can even work with fractions A, D, modulo M, as long as the denominator is relatively prime. So this is the part that confused me from last time I was reading this. As long as the denominator, D, is relatively prime to M. For example, we can compute 5 over 7 modulo 11. So 5 is A, 7 is D, 11 is M. By first observing that 7, which is D, times 8 is congruent to 1 mod 11. So we apparently had to find the inverse for 7 and 11 first, which I guess was 8. So the inverse of 7 mod 11 is 8. Then you do the full thing, I guess. So over here, I suppose then you do 5 over 7. Oh, equals, that's fine then. 5 times 7 inverse. Okay. So just 5 times, yeah, inverse 7. But which is congruent to 5 times, so I guess now we're using this 8 part. Which is, it just totally multiplies it, like 5 times 8. It's very interesting. So I'm going to make this red, and this red, and this green, and this green. So it's really clear where these numbers are coming from. And then like mod 11, obviously coming down from here. So then you obviously get 40, right? Maybe, does it show up well with red and green? And then you just do the 40, which has to be, I think what's helping me to understand this a bit is that whatever number you're getting, to make it mod whatever, it has to be lower than the mod number. So if you have 40 and you're trying to make it mod 11, it has to be less than mod 11, obviously. And then so obviously at the end of the day, you're trying to figure out wait, the whole thing equals 7 mod 11? 5 over 7 modulo 11 is 7 modulo 11? I feel like that's what this is saying, but now I'm going to have to ask. To be like, wait, so let me just write the whole thing down. So 5 over 7 equals 5 times 7 inverse. That makes perfect sense, which is congruent to 5 times 8, which is congruent to 40. Yep. Which is 7 mod 11. So is that saying that 5 over 7 is like, you know, congruent to 7 mod 11? I'm not sure. Seems like that's what it's saying, but, you know, always good to double check. I could just put a note here as well, but I'll keep it in these notes. Remark 1.15, in the preceding examples, it was easy to find inverses modulo m by trial and error. However, when the m is large, it is more challenging to compute the inverse modulo m. Note that we showed that inverses exist by using the extended Euclidean algorithm. So I'm going to take that note. Show that a negative 1 exists with E, A. And I guess I'm taking note in 3 places. So show
always interesting taking the notes here. A to the power of -1. Whoops, what did I do? A to the power, oh, because it's negative. Okay. In order to actually compute the u and v that appear in the equation AU plus MV equals the GCD of A and M, we could apply the Euclidean algorithm directly, as we did in example 1.10, or we can use a somewhat more efficient box method as described at the end of the preceding section, which in my opinion was pretty interesting as well, or we can use the algorithm given in exercise 1.12. In any case, since the Euclidean algorithm takes only 2 log 2b plus 3 iterations to compute GCD of A and B, it takes only a small multiple of log 2m steps to compute A inverse modulo m. We now continue our development of the theory of modular arithmetic. If A divided by m has the quotient q and remainder r, it can be written as, so we're here and we're saying that if A can be divided by m and has a quotient of, so basically A equals m when you multiply it by q plus r. And r is some value that's going to be between 0, it could be 0, right? And less than m. Because if it was m, q would just go up by 1. So this shows that A is congruent to R mod M. A is congruent to R mod M. Okay, I'm gonna have to write that down. I've already read through it, but now I feel like I have to actually try and remember. A is congruent to M. Oh wait, sorry. A is not congruent. A is equal to. A is equal to M multiplied by the quotient plus the remainder. And we already know 0 R M. Sorry, I'm taking notes on my side. So this shows that this is the part I wanted to get down. A is congruent to R mod M for some integer R, where R is between 0 and m minus 1. So if you want to work integers modulo m, it is enough to use the integers between 0 and m. Yeah, that's obvious. Okay, wait. That's obvious. Sorry. So we write this. This is called a ring. Yes, yes. I'll take this down, because this is kind of the part that, like, well, is it like math BB, I think? Let's see, just so that I can see if I remember. It's math BB, boom, and then math BB, boom. Hey, pretty. We always divide the result by m and take the remainder in order to retain an element in
Z star or whatever. Figure 1.4 illustrates the ring Z5Z by complete addition and multiplication tables modulo 5. If you studied ring theory, you'll recognize that ZMZ is the quotient ring of Z by the principal ideal MZ, and that the numbers 1, 0, 1, all the way to m minus 1 are actually coset representatives for the congruence classes that comprise the elements of Z modulus Z. For a discussion of congruence classes and general quotient rings, see section 210.2. So this is an addition and multiplication table modulus 5, which means you could only have the numbers 0 to 4 available. And I have not spent enough time, but like 5 times 0 all the way across 0, and it's like 1, 2, multiply 2, 4, you get 12. 2, wait, 2 and 4, I'm looking at the wrong one, I'm looking at 3 and 4, 12, you get 2, because 10, 5 times 2 is 10, plus 2 is 12, so yeah, relatively self-explanatory, and then you take 5, so 4 and 0, you're 4 away from, let's see, 2 and 4, 6, and then it's 1, because you're 1 over 5. There you go. So here, here you're taking the number, adding it, so 3 plus 4, and finding the modulus, and here you're taking, 3 times 4, and finding the modulus, and it's doing it for the entire grid. So proposition 113 tells us that A has an inverse modulo M if and only if the GCD of A and M equals 1. Numbers that have an inverse are called units. We denote the set of all units, oh, this is fun, by ZM star. Okay, that's what I was looking at. So A is an element of ZZM, where the GCD is of A and M is 1. So, and then A is an element of ZMZ, not ZM. A has an inverse modulo. This is also called the group of units modulo M. Notice if A1 and A2 are units modulo M, then so is A1, A2. Do you see why this is true? I guess because you're just creating a multiple of these two, and so they're just in this unit, I guess, or they're in this group or whatever. Group of units. I'm gonna sneeze. Achoo! Excuse me. My gosh. Okay. So when we apply 2 units, we only get a unit. On the other hand, when we add 2 units, we often do not get a unit. The group of units modulo 24 is 1, 5, 7, 11. Okay, so just the primes. The multiplication table for Z24 star, and then the group of units modulo 7 is all these wonderful numbers. And this is where it starts getting even more exciting and interesting. So since every number between 1 and 6 is relatively prime to 7, the multiplication table for Z7 star, I guess, is illustrated in figure 1.5. In many of the crypto systems that we will study, it is important to know how many elements in the unit group modulo M. This quantity is sufficiently ubiquitous that we give it a name. So, the totient function, Euler's phi function, Euler's totient function, a little zero with a cross through it, whatever makes people happy, I guess. So this is the number that lets us know how many numbers are in the group that are relatively prime to the number that we're looking at. So the totient function of M is equal to like the number in the set, which is like a number between 0 and M, where the GCD of A and M is 1 and A is in the middle of that. So the number has to be less than M. So we see from examples 117 and 118 that the totient function for 24 is 8 and the totient function for 7 is 6. So this is the unit group modulo 24. You can see a lot of numbers repeating, so you don't get every number. The unit group modulo 7, you do get every number. Yeah, I don't know why they're doing this. Modular arithmetic and shift ciphers. So they really want us to look at this shift cipher again. Recall that the Caesar or shift cipher studied in section 1.1 works by shifting each letter in the alphabet a fixed number of letters. We can describe a shift cipher mathematically by assigning a number to each letter, as in table 1.7. Then a shift cipher with shift K takes a plain text letter corresponding to a number P and assigns it to the ciphertext letter corresponding to the number P plus K mod 26. Notice how the use of modular arithmetic, in this case modulo 26, simplifies the description of the shift cipher. The shift amount serves as both the encryption key and the decryption key. Decryption is given by the formula. Take the ciphertext letter that you're at now, and that's going to be congruent. I keep using the word congruent. Yeah, that's going to be congruent to the plain text letter you're looking for, plus that secret key. And then you're going to go do this mod 26. And then decryption is you take the plain text that you actually have, that you want to get, and that's going to equal the ciphertext that you have, and then you're going to minus this kind of key that hopefully was given to you, and be mod 26. More succinctly, if we let P be the plain text letter, and I think I'm just going to take the note of this. I wonder what it's going to look like to just try and paste those things. Yeah, that wasn't going to work. If we let, I usually just do it like this. If we let this be this, P equals this, My gosh. I'm going to have to get off soon, I think. K equals secret key. And then I usually just go down one. Then you get all this fun stuff. Then C is congruent to P plus K mod. Thingamabobs. And then I'm just going to take out this. And P is congruent to C minus K. And then good job, everybody. I didn't really care much about like 1.2, 1.3, 1. Whatever, or 1.3 whatever. I think I'm just going to do it when I get to... Although for fast powering I will. Because I needed to take the notes on this one. And I might even... I'm kind of tired. So, let's see. 1, 2, 3. Fast powering. Yeah, getting a bit tired. But I'm finally feel like I'm getting into the swing of things. And so, I don't want to... But I do want to be like awake and like ready to go for the fast powering algorithm stuff. And it's pretty short. Then we get to prime numbers, unique factorization, and finite fields. Which I guess I'm going to finish tomorrow morning. Yeah. It's not too long. Fun stuff. Okay. I am going to... Oh my gosh, this thing goes ahead so quickly. Okay, let's just go through the fast powering. I'm going to try and be quick. In some cryptosystems that we will study, for example, the RSA and Diffie-Hellman cryptosystems, Alice and Bob are required to compute large powers of a number G modulo another number N, where N may have hundreds of digits. Okay. So large powers of a number G, so the powers of G modulo some large number N, where N may have hundreds of digits. The naive way to compute G to the A, right, these powers of G, is by repeated multiplication by G. You just, if you're doing G to the A, you just keep multiplying G A times. Thus, G to G1 is congruent to G mod N, and G2 is congruent to G. Okay, it just keeps going. It is clear that G to the A is congruent to G to the A mod N, but if A is large, the algorithm is completely impractical. For example, if A equals 2 to the 1000, then the naive algorithm would take longer than the estimated age of the universe. Clearly, if it is to be useful, we need to find a better way to compute A to the G mod N. The idea is to use the binary expansion of the exponent A to convert the calculation of G to the A to a succession of squarings and multiplications. An example will make the idea clear, after which we give a formal description of the method. Oh, that's cute. So far, so good. Relatively straightforward. Suppose that we want to compute 3 to this big power, 218, mod, 1000, so nothing crazy, but mod 1000. The first step is to write 218 as a sum of powers of 2. So you're adding up all these powers together. You have 2, you have 2 to the 3, you have 2 to the 4, you have 2 to the 6, you have 2 to the 7, and you write them all up as a sum, and you're good to go. Then 3 to the 218 becomes 3 to the 2 and then the 218 stuff. So pretty much that's what when it's saying like a binary expansion of the exponent. I'm actually going to maybe write this one down for myself.
So binary expansion of the exponent. You take the simple question of 3 to the 218, mod 1000. So that's the question, is compute this. Well, then you got to do 218 is equal to 2 plus 2 to the 3 plus 2 to the 4 plus 2 to the 6 plus 2 to the 7. And once you have that, then 3 to the 218 becomes 3 to the 218 is equal to 3 to the 2. And then in the exponent, you're doing 2 to the 3 plus 2 to the 4 plus 2 to the 6 plus 2 to the 7, which equals 3 to the 2 multiplied by 3 to the 2, 3. That's cool. Multiplied by 3 to the 2, 4. Multiplied by 3 to the 2, 6. Multiplied by 3 to the 2, 7. Notice that it is relatively easy to compute the sequence of values. So when you take this number in the front, you know you're going to have to compute it into powers of 2 for what you're looking to do. And you can tell that it's relatively straightforward to do as many as you need to. Since each number in the sequence is a square of the preceding one, further, since we only need these values modulo 1000, we never need to store more than 3 digits because we don't actually care about anything greater than 1000. We're only working modulus 1000. Table 1.8 lists the powers of 3 modulo 1000 up to 3 to the power of 2 to the power of 7. Creating table 1.8 requires only 7 multiplications, despite the fact that the number 3 to the 2 to the 7 does equal 3 to the 128, or despite that it has a quite a large exponent, because each successive entry in the table is equal to the square of the previous entry. We use 1.3 to decide which powers from table 1.8 are needed to compute. We use 1.3. What's 1.3? We use 1.3 to decide which powers are needed to compute 3 to the 283. 3 to the 218. Thus, so this is the table. This is the multiplications. Like 3 to the power of 0, 3 to the power of, I guess, 3 times 3, 3 times 3 times 3, and so on. Oh no, because you're doing it mod 1000. Yeah, so. Anyways. 6 square powers of 3 modulo 1000. These are all the mods. Very exciting. And so this is the value here. At the end. We note that in computing the product 9 times 561 times 721 times 281 times 961, we may reduce, oh nice, we may reduce modulo 1000 after every multiplication. So we never have to deal with very large numbers. We also observe that it is taking us only 11 multiplications to compute this very large number, a huge saving over the naive approach. And for large exponents, you save even more. So the real beauty is that as you compute each of these multiplications, you keep having the ability to go mod 1000. So I think like here,
you get a number larger than 1,000, but you only take the last few digits, and so on. The general approach used in example 1.19 goes by various names, including the fast powering algorithm and the square and multiply algorithm. We now describe the algorithm more formally. Okay, this is the part that I actually want to pay attention to. So we compute the binary expansion of A as A equals A0, A1 times 2, A2 to the 2 squared, and you do it as, again, binary expansion. Okay, and we assume that A to the R equals 1? Okay. I don't even know what that means. Because you're saying with A to the 0 to A to the R being 0 or 1, so they're just bits? Oh, okay. Okay. Yeah. So there's bits. It's all in binary. I get it. Yes, yes, yes. To make it faster, we assume A to the R equals 1. 1 times. Okay, compute the powers G to the 2I mod n by successive squaring. A1 so when you have A0 and G, each term is the square of the previous one, so this requires R multiplications. Where's my G? 3 is your G. G to the A. A is your number. To get this G to a large number, it's congruent to square root of the previous round. So the previous round squared is congruent to this squared. The previous round squared is equal to this squared again. The previous round squared is equal to this squared. Okay. Compute G to the A mod n using the formula. So G to the A, we know we're mod n. You have all these A's. This looks more interesting. So you go G to the A for round 1, G to the 2. A1, G to the 2, 2, A2, G to the 2, 3, A3.
Note that the quantities, right, A0, A1, A2, A3, were computed in step 2. Thus, the product can be computed by looking up the values of AI, of the AIs whose exponent of the capital AI is 1, and multiplying them together. I have no clue what that's talking about. I have literally no clue what it's saying right now. I'm going to have to go back, and obviously I have to implement the fast powering algorithm, and that's going to be a whole shebang. I guess tomorrow. I meant to have more time today for this, but... And, like, that's it. Literally. That's it. All of a sudden, it jumps into prime numbers and stuff. So, running time, it takes at most 2R multiplications, modulo n to compute. Since A is greater or equal to 2R, we see this takes at most 2 log 2A multiplications. Thus, even if A is very large, easy for a computer to do, efficiency, there's various ways in which it can be made more efficient. Okay, so now we need to go through 1.4 and 1.5, which I will go through tomorrow morning. I'll try and do it nice and early. I have this setup here, so there's no excuse for not getting it done bright and early tomorrow. And then, directly after that, I am going to do my best to try and tackle the actual exercises. So let's see, if we go to session 10 notes. So there's recalculate the extended Euclidean algorithm on the inverse of 397, or on the inverse of 397 in the group modulo 3257 with the tabular method. I do want to try that out tomorrow. Kind of like stream, take the notes, then go to my tablet and just try and write it out. Implement the fast powering algorithm for big ints. That's just something I need to spend like an hour with, or maybe a couple hours with, and just like try and get it done. Try and figure out how to, and like, wait, let's open it exactly. Because for fast powering, my difficulty is always like, what are you supposed to be getting? Right? The fast powering is the idea that you can use a number, like, you can do it on numbers much larger, like big ints. And so you're just trying to compute this, right? I guess there's no remainder still, though. Mod 1,000. So you only want the first 1,000 digits, because you're always cutting off the rest. Well, sorry, not the first 1,000 digits. The first, like 3 digits. See, they make it sound so simple, but I'm sitting here like, how do you get those powers? Like, it's not that easy. Compute the binary expansion of A. Compute the powers of G to the 2 for each round. A is congruent to G. This is super confusing to me, but that's okay. Compute G to the A using the formula, and you can like square each time.
Anyways, I gotta compute that, which sounds like a fun couple hours of my time. And then for positive A and B, suppose that you have U and V that does satisfy this. Prove that the GCD equals 1. So this one again is asking you to do a proof. In my opinion, there's actually a proof in the textbook, so maybe I just need to find that. 1.18, suppose that g to the a is congruent to 1 mod m, and g to the b. Okay, so you have g to the a and g to the b are both, and prove that g to the GCD of a and b is congruent to 1 mod m, and there's already a proof for that in the book as well, but again, trying to get us to write proofs, I need to, like, that's a whole different thing. I'm going to skip these two probably, but using a program, obtain a generator for the group of integers. These two, both values are prime. What method you use to check if the candidate was a generator? So to me, I suppose you would, they're prime, so the GCD of these two numbers is 1. And I guess this to me is actually the difficult part. I was talking to Thor about it. He did provide me some feedback, and so that'll help me with that question. So again, tomorrow morning, bright and early, I will be finishing chapter 1 finally. Then I'll be kind of going through some handwritten math, and just doing some little programming in Rust. This is actually probably where I should start with the programming in Rust, but to me this is just implementing a very well-known algorithm, which is kind of just like put my head down and do it, whereas this is like think for myself and figure out how to do something. So I need a little more help with that, but that is it for today. The last thing I will do is see if my term is working. So there you go. I think I can just get maybe get commit. Maybe got to ch 1.4, I think. So I'm starting from 1.4, 1.5. Finish 1.4, 1.5, 1.5 tomorrow, plus start exercises. And then I'm not sure if this will work. It should work, maybe. Oh, look, it worked. Get push. Okay, well, that is about it, ladies and gentlemen, and whoever else might be probably not watching. But yeah, I am tired now, and so I am going to just decompress my brain for a bit and figure out what Thor was talking